Hmm. Okay, students. My name is Palak Patel. I'm working in the Mahatma Gandhi Institute of Technical Education and Research Center, Navsari, in Civil Engineering Department. I'm going to teach you the design of structures 3150612. This is the subject code, and this subject is taught in the BE third year, SEM 5th. So in this lecture, we are going to learn shear reinforcement. So shall we start? What is shear reinforcement? Shear reinforcement is used for the resist shear force. Shear force means a simple reaction. Oh, sorry, a reaction on the structure. What type of reaction? If you see here, it's your beam. It's a one-line drawing, and it's a point load here, and this is supported on column. At that time, by this load, you can found a reaction. Okay, if here is UDL load, then same phenomena formula here. Here is reaction. So this type of reaction we call this as a shear force. Okay, here is a two condition. First is simply supported beam, and second is also simply supported beam. But here is at ends and at mid span. At ends and at mid span, and these are the bending moment at end and shear force at end for UDL load. If assume here is your UDL load, so your reaction is at the end is WL by 2, but the bending moment is 0 at the end. And same concept here at the mid span means at here. So at the mid span, bending moment is WL square by 8, but a shear force is 0. So if you're going to design a shear reinforcement, you have to provide shear force at the ends. We not need to provide a shear force at the center. Okay. So which are the shear reinforcement provided in the beam? So we have two types of shear reinforcement which provided in the beam. The first one is stirrups, and second is bend. Okay, so let's start. So here is a shear reinforcement nominal shear stress. Nominal shear stress tau V is equal to Vu upon Bd. You can find out easily by this equation Vu upon Bd. Vu is a shear force, B and D is a width and effective depth. Tau V is equal to nominal shear stresses which generated in the beam. Okay, vertical stirrups. We have types of stirrups. We have two types of stirrups. First is vertical stirrups. Second is inclined stirrups. So what is vertical stirrup? Vertical stirrups means there is your beam. Here is your beam is resting on column. At that time, your stirrups is provided like this. Inclined stirrups means your stirrups is provided in this angle, 45 angle at the support is called inclined angle. And in the vertical stirrups, we have a two-legged, four-legged, and six-leg stirrups. So what is two-legged, four-legged, and six-leg stirrups? I will explain it here. Give me some time. Okay. Look at here. It's your beam cross section. Okay. Is beam cross section. Here is a reinforcement. So what is two-legged? Its stirrups is running, and this called two-leg stirrups. Okay. And what is four legs? Your one stirrups here is two leg stirrups, but one more stirrups is follow in this direction. It's called four leg. You can see one, two, three, and four leg. So these are two legged, these are four legged. So in the four legged we have a two stirrups here. This first one, here is second one. At the same point, at the same point. There is a second. So here is we have a six leg stirrup. First stirrups you can see here. Second stirrups here, and one more. Okay, here is six leg. One, two, three, four, five, and six. Okay, so this is called a two-legged, four-legged, or six-legged stirrups. Then after we have to design a shear enforcement. So how we design shear enforcement? So first of all we have find out tau v. We can find out tau v by a shear force Vu upon Bd. Tau v is a nominal shear stress. Okay, after calculate tau v we have to find out pt. We can find out pt by ast. Ast means area of steel in a tension zone. Area of steel in a tension zone. So by the pt we can find out tau c. This equation is by this table. Okay, when we find out pt, so by the pt value we can find out tau c value from this is code. Okay, and then after tau v and tau v and tau c we have to compare this both the value. Okay, and if we have the two cases here, here's the first case is tau v is less than tau c. Tau v is less than tau c, or second one is tau v is greater than tau c. We discuss both condition here. So if tau v is less than tau c, that time provided minimum shear reinforcement. Okay, minimum shear reinforcement. So this is the equation for minimum shear reinforcement. SV is a spacing. SV is spacing. ASV is the area of steel at a stirrups. So how we found ASV? ASV we can find out. Assume we provide 8 mm diameter bar at stirrups. So if we provide 8 mm diameter bar, ASV is pi by 4 into 8 whole square. These are the ASV. But if your stirrups is two-legged, that time we have to multiply by 2. Okay, so ASV equation is pi by 4 into 8 whole square into 2. Okay, if is 4 leg stirrups, then it multiply by 4. If it's 6 leg stirrups, multiply by 6. Okay, 0.87 Fy is the steel grade which we use for the stirrups. Okay, then after 0.4 D or 0.4 D. Okay, these are the equation for the minimum shear reinforcement. Look at here. Then second case is here, tau v is greater than tau. At time we have to compulsory design a shear reinforcement. Compulsory we have to design a shear reinforcement. So that time we have to shear reinforcement. You can find out by Vu minus tau c upon Bd. These are the shear force resist by concrete. Vu minus tau c dot into B into D. Okay, this shear force is resisted by a concrete, and this is the total shear force. This is a total shear force. Okay, if assume we have a total shear force is 120 kilonewton. Total shear force is 120 kilonewton. But some portion is resisted by a concrete. If I can say it will resist by a 50 kilonewton. 50 kilonewton. At that time, 70 kilonewton force. 70 kilonewton force. It will be resist by a. It will be resist by a steel. Okay, and that time we have to design a shear reinforcement for 70 kilonewton. Okay, understood? And then the second condition here, your shear reinforcement is shear force is resist by stirrups, but we provide a bend up. We provide a bend up. At that time, this equation is here. VUS1 is equal to 0.87 FY ASV sine alpha. VUS1 is equal to 0.87 FY ASV sine alpha. So by this equation, we can find out a shear force which resists by a bend up bar. Okay, let's assume there is a 120 kilonewton shear force. 50 kilonewton is resisted by a concrete. Okay, so we have to 70 kilonewton force which can be resisted by steel, but in the 70 we provide a one bent up, so 20 kilonewton force is resisted by a bent up bars. So remaining 50 kilonewton force is resisted by a stirrups. Okay, so when we design a shear reinforcement, means we design a stirrups, then we have to use this 50 kilonewton force. Okay, so when we find out the VUS1, we have to VUS minus VUS1, then we get a net VUS. Okay, so this is net VUS. We can call this as the shear force which must be resisted by stirrups. Okay, then after this equation, then after this equation 0.87 Fy ASV D upon VUS. By this equation we can find out a spacing between stirrups. Okay, so our design is completed. So after a completed design, we have to follow some check for a maximum spacing. Maximum spacing which we can provide it. Okay, so we got first value is SV. Here is a first value SV1. We call it SV1. Second value 0.75D. Third value 300 mm. And the last one SV minimum. Okay, so by this four value, whichever is smaller, we can take this value as the spacing. Okay, First example is starting here. First example, a RC beam 250 by 500 mm, effective, reinforced with four numbers of 20 mm diameter of Fe415. The beam carries factor shear force 200 kN. Find spacing of 8 mm diameter, two-legged Fe250 stirrups. Use M20. So what is given? So we have one beam which width is 250, depth is 500, and we have four numbers of bar of 20 mm diameter. Steel grade is Fe415, and we have a factor shear force 200 kilonewton. Factor shear force is Vu is given, and we have to find out spacing means SV for 8 mm diameter two-legged, and this grade is 250. So let's start the design. Yep. So factor shear force is given 200 kN, FCK 20 Newton per mm square. So first of all we have to find out tau v. Tau v equation we have Vu upon Vd. So Vu is equal to 200 into 10 raised to 3 divided by 250 into 500. 250 into 500. So tau is 1.6 Newton per mm square. 1.6 Newton per mm square. So we found the tau v. Then after we have to find out tau c. For the tau c we have to find out pt. So by the AST, area of steel in a tension zone, we can find out pt, percentage of steel. So AST is 4 numbers of bar of 20 mm diameter. So 4 into pi by 4 into 20 whole square. So AST is 1256 mm square. These are the area of steel at a tension zone. Then after PT, 100 AST upon BD. So 100 into 1256 divided by 250 into 500. So PT by this equation is 1. AST we find out, B and D is given. So 1. So by the IS code page number 73, we can find out tau c. There is a table, you can see table number 90. We can find out tau c from this table. So we find out PT, 100 AST upon BD is 1. 100 AST upon BD is 1. PT is 1. Okay. And the concrete grade is M20. So by the 1, we have to follow this row, and for the M20, we have to follow the second column. So your value is 0.62, 0.62. So tau c is 0.62. So here we have a tau v is more than tau c. Tau v is more than tau c. So by this condition, we have to design a shear reinforcement. So we have an equation VUS is equal to VU minus tau c BD. So VU is equal to 200 into 10 raised to 3 minus 77500. Tau c we can find out from here, tau c into BD. Tau c is 0.6, B and D is 250 into 500. So put the all value in here and we get VUS 1225005. Sorry, 12250 Newton. So this VUS, it's a shear force. Okay, VUS, it's a shear force which we have to resist by stirrups. Okay, so this is the stirrups. 8 mm diameter bar, two-legged mild steel vertical stirrups. This condition is given in the example. So first of all, we have to find out ASV 2 into pi by 4 into 8 whole square. So ASV is 100.53 mm square. So by the ASV, we have the equation for the SV. SV is spacing. SV is spacing. Spacing is equal to 0.87 Fy ASV D upon VUS. Okay, 0.87 is here. Fy is 250. Fy is steel grade which used for the stirrups. Okay, so in this example we have to use 8 mm diameter bar, two-legged mild steel vertical stirrups, and its grade is Fe 250. So Fy is 250, ASV 100.53, depth 500, VUS we found out 122500. So SV is 89.24 mm. 89.24 mm. And then the thief condition here. Three condition. 0.75 into D. 0.75 D is 500. So spacing is 375 mm. Second is 300 mm. Third is SV is equal to 0.87 Fy ASV upon zero point 0.4 into B. So is zero point 0.4 into B. So this is a SV minimum equation, minimum spacing equation. So 0.87 into 250 into 100.53 divided by zero point 0.4 into 250. So SV is 218.65 mm. These are the minimum spacing. These are the minimum spacing SV. So we provided SV 89.40 mm. Okay, whichever is smaller between these four, we can provide it as a spacing. Okay, so let's start a second example. Okay students, so we have the second example. The simply supported beam 250 by 500 mm effective is supported on 5 meters span and subjected to total service UDL 40 km per meter over entire span. Four numbers of 22 mm diameter tensile bar are provided. Design shear reinforcement use M20 concrete mix and Fe415 steel. So the longitudinal section and cross section with details of reinforcement. Take gamma F is equal to 1.5. So let's start to calculate the example. Width of beam is 250, depth is 500, FCK 20 Newton per mm square, Fy 415 Newton per mm square. Okay. Then after assume effective cover 50 mm. We assume effective cover is 50 mm. So that's why we have capital D. Overall depth 500 is effective depth. 500 plus 50 which effective depth plus cover is equal to 550 mm. Okay. Then after second one is density of concrete 25 kilonewton per meter cube. Okay. Self weight of beam, we have to find out self weight of beam. Why? Because here is only given load, is total service UDL is given. So we have to add self weight of beam. So 0.25 is a breadth of width of beam into 0.55 is depth of beam, overall depth of beam, or 25 or multiply by 25 is density of concrete. By this equation we got a self weight of beam is 4 kilonewton per meter. Okay, 4 kilonewton per meter. Then after service load 40 kilonewton per meter. Service load is given 40 kilometer. So 40 plus self weight 4 kilometer. We got total load 45 kilometer per meter. Okay, 45 kilometer per meter is total load, UDL load. Okay, so we need a factor UDL. Factor UDL is 44 multiplied by 1.5. So total factor UDL is 66 kilonewton per meter. Okay. Then after by this UDL, we have to find out shear force VU. So shear force is find out means we have to find out reaction at A and reaction at B. So VU is equal to WL by 2 is equal to 66 into 5. 5 is the length of beam. So 66 into 5 divided by 2, we got 165 kilonewton. So these are the 165 kilonewton. It's the shear force. So by this shear force, we have to find out tau V. Tau V is equal to VU upon BD is equal to 165 into 10 raised to 3 divided by 250 into 500. Divide by 250 into 500. So by this tau V value, we got 1.32 Newton per mm square. Okay, these are the tau V. Then we have to find out tau C. So for the tau C, we need a PT percentage of steel. And for the percentage of steel, we have to find out area of steel at a tension zone. So 4 into 22, 5. 22 is the diameter of bar. 4 numbers of 22 mm diameter bar is provided at a tension zone in a beam. So 4 into pi by 4 into 22 whole square. So area of steel at a tension zone 1520 mm square. By this area of steel at a tension zone, we can find out PT. PT means percentage of steel. So 100 AST upon BD. 100 into AST is 1520. B and D is 250 into 500. So percentage of steel is 1.216 percentage. 1.216 percentage. So then after we need to find out tau C. So we have to follow once more the IS code is here. Okay. So for the tau C value, we have to follow table 90. Table 90. So table 90, we have to PT value here. Here 100 AST upon BD. So for this column, we have to find out PT. So 1.2.1. Your value is in between these two value, and concrete grade is M20. So your value is 0.62 or 0.67. In between these two value, you can assume any value. So I assume tau C is 0.66 Newton per mm square. Okay. So look at here. First condition, tau C is greater than tau B is greater than tau C. So by this condition, we have to design shear reinforcement. Compulsory, we have to design shear reinforcement. We have to design shear reinforcement. So we need a VUS. So VUS is equal to VU minus tau C BD. VU minus tau C BD. So VU is equal to 1.165 into 10 raised to 3 minus tau C is 0.66 B is 250, B is 500. VU is total shear force and VUS is 82500 Newton. So this VUS is 82500 Newton. This shear force is resisted by stirrups. So we have to design a stirrups for the resist 82500 Newton. So at this condition, we consider two legged 8 mm diameter bar, a vertical stirrup of FE 250 grade. Okay, this data is assumed by us. Okay, if this data is not given in the example, then we can assume this data. So ASV 2 into pi by 4 into 8 whole 8 square. 2 means 2 legged, 8 is diameter of bar, 2 into pi by 4 into 8 whole square. So ASV is 100.51 mm square. 100.51 mm square. So SV is 0.87 Fy ASV D upon VUS. So this SV gives us spacing 0.87, Fy is 250, ASV we find out here 100.51, depth is given, effective depth, and VUS is 82500, which is resisted by stirrups. So our gate spacing between stirrups is 132.49 mm. Okay. Then after we have to find out check a maximum spacing. So here is maximum spacing is 0.75 into D. Okay, 0.75 into 500 is equal to 375 mm. 2 is a 300 mm, and the third one is SV is equal to 0.87 Fy ASV divided by 0.4 B. So by the SV we got a value 281.6 mm. 281.6 mm. So by this 4 value, whichever is smaller is provided as a spacing. Okay. So we provide SV is equal to 132 mm center to center spacing for the two-legged 8 mm diameter bar. Okay, look at here. Here is a figure. It's vertical stirrups here. Vertical stirrups, two-legged. Vertical stirrups, two-legged. Okay. Here is the spacing 132 mm. B is the 250 mm width and depth is given. Is the cross section. Is the longitudinal section. Okay. So this design is completed. One design is completed. The second, this is the last one. The reinforced concrete beam section 300 by 450 mm is reinforced with 3 numbers of bar at 20 mm diameter bar of Fe250 at an effective cover 30 mm. At an effective cover 30 mm. The shear force at a section is 140 kilonewton. 140 kilonewton. Design shear reinforcement considering 120 mm diameter bent up at 45 degree. So in this example we have one bent up. So your shear force can be resisted by this bend up. Okay, and use M20 grade cement and stirrups 8 mm diameter bar of mild steel. So let's start. Okay, here width is given 300 mm, depth is 450 minus 300, so 420 is effective depth. FCK 20 Newton per mm square, Fy 250 Newton per mm square. Shear force is given, so we have to calculate factor shear force 1.5 into 140. So 210 kilonewton is a factor shear force. So by the shear force, we have to find out tau v. Tau v is equal to Vu upon Bd. Vu is shear force 210 into 10 raised to 3 divided by 300 into 420. So tau v is 1.67 Newton per mm square. 1.67 Newton per mm square. Then we have to find out tau c. So for the tau c we need AST and PT. So three numbers of bar of 20 mm diameter. So AST is 942 mm square. So by this AST we have a PT is 0.75 percentage. 0.75 percentage. So by this PT value we can find out tau c. By this PT value we can find out tau c. So look at here 0.75. So this row, so your value is 0.56 M20 grade cement. So 0.56 tau c. Tau c 0.56. And by this both the value tau v and tau c, we got tau v is greater than tau c. So by this condition we have to design shear enforcement is compulsory. So same condition here, found that VUS equation VUS minus tau c into BD. VU is 210 into 10 raised to 3 minus 0.56 into 300 into 420. So VUS is 139,440 Newton. Okay, and here we have one bar is bent up at 45 degree. So some shear force which is here 139,400 Newton. This shear force can be resisted by this bent up. So you can see we discussed earlier here your shear force can be resisted by stirrups and as well as bent up bar. Okay, here we have a one bent up bar here, but this 139,400 this shear force is resisted by stirrups and bend up. Okay, so I can see there is a one bend up is provided, so some portion of this shear force 139,440 Newton, this shear force is some portion is resisted by a bend up. Okay, so we have to find out this shear force which resists by a bent up bar. VUS1 is equal to 0.87 Fy ASV sin alpha. ASV sin alpha. Fy is 250. ASV pi by 4 into 20 whole square. Why? Because we have a one bent up bar. So this type of we have to use shear ASV for the bent up bars pi by 4 into 20 whole square. So ASV is 134.50 mm square. Alpha is 45, which angle is given. So VUS is equal to 0.87 into 250 into 314.50 sine 45. So VUS is 448,315.0 Newton. 315.0 Newton. So here is one condition, VUS1 is lesser than 0.5 VUS. This condition is fulfilled here. 48315 lesser than 0.5 into VUS is here 139440, 139440. So by this condition, your shear force can be resisted by a bent up, so we have to find out net VUS is equal to VUS minus VUS1. So we have this value 91125 Newton. So this is the shear force which is resisted by a stirrups. Okay. So we have to find out spacing of vertical stirrups. So here is equation SV is equal to 0.87 Fy ASV into D minus net VUS. So SV is 100.75 mm, 100.75 mm. So we have find out these three values: 0.75 D, 300 mm, SV is 0.87, Fy ASV divided by 0.4 D, 0.4 B. So by this equation we have the value 182.70 mm, 182.70 mm. So we have to provide a smaller value, so 100 mm is smaller, so we provide a 8 mm diameter bar, 2 leg stirrups, mild steel vertical stirrups at 100 mm center to center. You can see here spacing is 100 mm center to center. Okay, here is a one bent up bar. Okay, so our figure and example is completed. Our example is complete. So our shear enforcement design example is completed. Our shear enforcement chapter is completed. In the next lecture, we start a one-way slab design. Okay. Or then after we will start a one-way slab design, and then for take care and bye.